Welcome to the Mechanical Design Tutorial Part 2. Today we're going to be focused on concept sketching and conceptualizing our design. So what does that mean? That's like placing parts of our design. How tall is it going to be? How big is it going to be? How wide is it going to be? Um, like where are things going to go? Meaning like where is our gearbox going to go? Where are we going to place pulleys and belts and stuff like that to transmit power? Where are we going to place the hardware to mount all of this stuff? We're going to conceptualize all of this, and we're going to suss all of this stuff out before we go and manufacture this stuff for real. This is going to help us in the actual design process. It's going to make designing our our goalie more straightforward if we do like conceptualization. All right, so part two, concept sketching. So what is the goal? I'm gonna start today off actually by showing you guys the goal for the goalie. Um, why? So that everybody can have a clear understanding of what it is we're working towards and what I'm seeing, what I'm envisioning when we want to, when I'm conceptualizing these. So I've already done the design for this project. That's what you see here. And basically, this is based off a concept sketch and a conceptualization that I did last week. This is a pretty simple design. So you can see this is my bicep, this is my forearm, my elbow is here. Um, there's a tube here. This mounts onto the frame. So one thing to keep in mind, we are doing this off of existing goalie frame. When I say an existing goalie frame, we have a goalie frame that lives in our shop right now. It's big. It's about the size of a normal goalie. It's wearing the goalie equipment that we're going to use right now, actually. And it is made out of a steel skeleton. So the skeleton is made out of inch and a half steel tubing. It creates a spine, and then there's also inch and a half. The same tubing is used to make the shoulders and the arms. We are going to chop the arms off, and we are going to mount this uh, onto those shoulders. So basically, this is a 2x2 aluminum tubing, square tubing, and the inside, the inner, you wouldn't call it the inner diameter because it's not round, but the internal width is an inch and a half. So we can basically just stick the steel round tube into that hole, and it'll fit nicely. And that's why I've got these bolt holes on top also, so we can bolt down into it to keep it nice and rigid and in place. So, what else is interesting and important about this design? You can notice that I've used pulleys instead of gears or chain. Why? This is to not, we want this to go inside the goalie equipment. This is not going to shred the goalie equipment, so this is better. Whereas a chain or a gear might get caught on the actual goalie equipment, and it's just going to rip it apart. Um, I've tilted the gearbox. I've put this slot. These are both in an effort to give us some wiggle room for belt selection. So basically, belt selection is dependent on the distance from the center to center of each pulley. And by adding this slot, we can pull and tension the belt by rotating the gearbox. And that's going to allow us to have some wiggle room in our belt selection. So in terms of design and manufacturing. Gearbox is on an angle for two reasons. So one is so that I can actually have this slot. Two is so that the motors are horizontal. Basically, the more horizontal the motors are, the easier it is going to be for us to make that cutout in the back of the goalie equipment, so that these motors don't like protrude, so that the motors can protrude outside of the goalie's equipment. And yeah, that's all there is really to this design. So let's take a look at the concept sketch I used, and then we're going to make our own concept sketch. So this is the concept sketch I created for this design. It's representative of the goalie, and it's meant to be representative of its general size. I use this so that I could basically figure out how long I want everything to be and where I want it to be placed so that it covers a sufficient amount of the net. Um, Keep in mind that when we do ours, our numbers are actually going to be different than these because this is small for an actual goalie. You can see I've drawn the net. I've drawn the goalie on the center line. I drew the arm. I placed it at some specific angle. I put some specific angle in the joint. And I have our overall length here, which is important for how much it's going to move. Sorry, for how much torque needs to apply to move it. And yeah, there's not too much to this design. It's pretty straightforward. So let's get into make on our own and see how it goes. Don't save. So I'm just doing this in SolidWorks for no particular reason other than we're doing everything else in SolidWorks, so I'd like to keep it in the same tool. And also, um, SolidWorks works well for this. There's better tools for this, but SolidWorks works pretty good. So let's start by drawing the goalie net. So it's 6 feet wide by 4 feet tall. And the tubes that make up the outside of the goalie net are 1.5 inch steel tube. What's going on? So we can put that in here. Sorry, 2.5 inch, 2 inch, 2.5 inch steel tube, like that. I'm just gonna extend these lines down here to meet up with the others, just because this is gonna represent our ground. And then I'm just gonna trim away these lines at the bottom. So trim, trim. And here is our net. I'm gonna draw a nice long center line so that I have a center line to fix stuff to. And then I'm going to start by doing a big rectangle that's going to represent the overall height of the goalie. So I'm going to say that our goalie stands about 6 feet tall. We're probably going to end up making it shorter than 6 feet tall. The reason for this is the shorter it is, the lower the shoulder is, which means the more of the net it can cover. But we don't want it to be too short and we don't want it to be too tall. So we're going to start with 6 feet and we can always go down. So 6 feet. And I'm going to make this the width of, I'm going to say probably a foot. The reason I'm using a foot here, goalie wears a helmet. I don't want to have to draw more squares than I have to, or more rectangles than I have to. So the goalie's helmet is no more than a foot wide. I know it's actually way less than a foot wide. It's probably close to 8 or 9 inches. So we can live with a foot. Also, its head is probably about a foot tall. So we're actually going to draw in the torso now. And we're going to do that just with another rectangle. But this time we're going to dimension that rectangle relative to the head. Oh my, this rectangle is way too big. So we're going to dimension it relative to the head. So I mentioned it's going to be about a foot off the top of the head. So let's do 1 foot. This rectangle is going to be the width of its shoulders. So with the equipment, we approximated it to be about 2.5 feet. 2.5 feet wide, probably 2 feet wide. 2.5 is probably a little bit too big. And then the pads that live on the goalie's legs, they stand 2.5 feet tall, or about 2 feet tall, and they're about 3 feet wide. So let's draw those in now. Yeah. So this is pretty representative of what the goalie's going to look like in standing inside the net. Now, keep in mind this doesn't have the arms. There's another thing I want you to keep in mind is this is actually not completely representative of what the goalie is like standing in the net, because the goalie doesn't actually stand in the net. If you've watched hockey, or if you've played hockey, or if you don't know hockey, this is still valid. The goalie never actually stands on the plane of the net. One, it would be very difficult because the net's there, so you can't really stand on the same plane as the net. Two, you typically stand in front of the net with good reason. We live in a 3D world, so when you look at things, there's perspective. So the goalie actually appears to cover more of the net the further in front of it they are. So if the goalie's standing a foot or two in front of the net, he appears bigger than he actually is in the net. So we need to keep that in mind when we're drawing this. That although right here it doesn't seem like the goalie's covering a lot of the net, there's like this whole area here. It does cover a very significant portion of the net, especially when we have the goalie a foot in front of the net. And the same goes for the arm and the rest of the goalie. These pads are also not fully representative of what goalie pads are like. The goalie doesn't stand with his pads closed. He stands with his pads a little more open like this. Um, because his stick lives on the ground, and also standing straight up in hockey, like one, you're gonna get knocked over. Two, it's not as stable as spreading your legs. Uh, Three, like the lower the goalie is, the more of the net he actually covers. Um, so that too. And our goalie frame, the frame I mentioned, is already bent over a little bit, and his pads are separated. So yeah, we're not gonna draw it in, but just keep that in mind as we're going. So let's start by drawing. Let's start by drawing the left arm. This is going to represent the glove arm. We're gonna put the glove on the left. So I'm just gonna start by drawing two lines, and then I'm gonna put the specific angle between them. So the angle I want between them is 135 degrees. I chose 135 because it's an easy to manufacture number, and I know if we don't manufacture this part, the part that's gonna hold the two tubes together, um, it's pretty easy to purchase. 135 is pretty common angle, and we're gonna set the size of these two tubes. So the first tube, I'm gonna set it to 450, and the second tube, I'm gonna set it to 400. Now I already know ahead of time that these two numbers are gonna result in a tube that is about 800, yeah, 800 millimeters long. I'm gonna leave this driven so that it doesn't break the design. Plus, we want it just as an overall measurement, not to actually drive anything. Um, so notice right now that the arm covers a good portion of the net. You gotta remember the arm's not just like this little stick arm. It's gonna have thickness too. Um, it covers a significant portion of the net right now, which is good. But ideally, we probably wanted to cover more, so we might end up making these lengths longer. So I'm going to put the arm in some specific positions right now so that we can see how it looks and what it's going to cover in different positions. So at 5 degrees to the body, this is almost at the bottom. You can see we're not covering very much, just like this area here. I'm actually going to make this a little bit longer. Yeah. And you can see we cover a bit more now. So if I go out to 10 degrees actually, we're covering a good chunk of the net. At 15, we're covering more of the net. You see like this. 20 degrees. We're covering a good part of the net. 25. So you can see as we sweep through the range of motion, we cover a very significant portion of the net. Let's jump 15 degrees. There is a point at which we stop actually covering the net. It's at about 60 degrees. I think it's 60 degrees, yeah. Only the elbow is left in the net. If I go another 5-10 degrees, it's going to go right out of the net. There's not much we could do about this. The only thing we could do about this is make the goalie shorter. So I am going to make him shorter. I'm going to make him 5'8". And I'm going to position his shoulder a specific height from the top. So this is supposed to represent the top of his shoulder pads. Obviously, his shoulder joint doesn't live right at the top of his shoulder pads. So I'm going to put it 10 centimeters from the top there. And you can see now at 60 degrees, we're still covering a good chunk of the net. We're covering the top left corner. If I go back down to 45 degrees, still covering a good part of the net. And at 30 now, covering a pretty large part of the net, which is nice. So we're gonna live with this configuration of the arm, where it's placed, how long each segment is, and the angle between them. Now keep in mind, the placement of the shoulder is not super dictated by us. It's actually more dictated by the frame that we're mounting this to. So some things like that we don't really have. we don't really have control over. Um, but we can dictate some stuff, like the overall height of the goalie and stuff like that. If we had to, we can adjust the overall height of the goalie. Um, if the goalie's shoulder was very low, we could technically modify the frame to make it taller. That's why we do these concept sketches, so we know how much taller we want it to be. But if it's within a similar range, so it is within a similar range, we just kind of live with it. I believe the goalie's shoulder is like, if the pad lives a foot below the top of his, or a foot below the top of its head, the shoulder is about 10 centimeters below that. Like the actual shoulder tube, the center of that tube is about 10 centimeters below that. Okay. Sorry. So this is our concept sketch. Now we understand basically where the goalie is going to live in the net, where his shoulder is going to be placed, and how long each section of the shoulder is going to be. Now we can move on to actually conceptualizing the hardware that we have to design. So we're going to start by conceptualizing the shoulder plate. Now, when I say the shoulder plate, I'll show you what I mean. The shoulder plate is this one that the gearbox mounts to. I'm going to talk about like placing all of these parts, placing this gearbox, calculating the belt lengths, all of that good stuff. So let's get into it. So I'm going to start a sketch with a representation of that steel tube in our design. So I'm going to actually just draw a box and make it for, actually I'm going to draw a line because it's easier to make them for construction. Okay. So I'm just going to dimension this really quick. So it's 1 inch this way and 1 inch this way. And then I'm going to put this distance is 15 millimeters. And this distance will get set in a minute. So this is a representation of that square 2 inch by 2 inch tube. We're going to put a hole here. This is going to represent our bolt holes. So for all of our bolt holes, we are going to stick to metric fasteners. Why, you might ask? Metric is a much simpler system to manufacture for, especially for fasteners. We tend to use metric fasteners in everything. All of our designs feature metric fasteners. If you ever want to tap a hole, metric is a way easier system to understand. So if I have a M4 fastener and it has a 0.5 millimeter pitch, that means the distance between the teeth. I take a 3.5 millimeter drill bit to pilot that hole, and then I run my M4 tap through it, and then I have a hole that's perfectly sized. Or sorry, a tapped hole that's perfectly sized. With Imperial, you have to go find the drill chart and find the specific drill that you need for that specific tap. For certain sizes, you need like letter drills. For certain sizes, you need number drills. For certain sizes, you need just normal drills. The Imperial system's too convoluted. With the metric system, it's way easier. You just take your bolt, you subtract the pitch from it. That's your pilot hole. You run the tap through it. You're done. So we're gonna stick to metric. I'm gonna make these 6 millimeters. That's 6 millimeter bolt hole. So that would use a M6 bolt. I'm gonna pattern this along this axis here because I need more than just one bolt hole. I'm gonna separate them by 20 millimeters each. Realistically, I could separate them by more. I could do like an inch. I'm gonna try and keep everything metric here as to not confuse anybody. And mix up my systems. Plus, Yeah, like realistically, if I did Imperial everything, it would be easier to manufacture on the machines we have at the machine shop. However, I'm designing this for CNC. I'm designing the whole design for CNC. So this plate is going to be designed for CNC. That tube is going to be designed for CNC. So, or even water jet. So really, the dimensions can be arbitrary. They can be whatever, but I'm going to keep them to just a standard metric dimension. Okay. So I'm gonna set the tube so that it's equal distance on both sides. Um, so that means that the tube ends here. When I say the tube ends here, I'm talking about this face of the tube relative to this hole is 15 millimeters. So basically, this part of the tube would stop here. The reason it doesn't on this design is because I have some extra holes, so I've just moved it back and forth. But don't worry about that. Nope, wrong one. Oh my god. Okay. So let's place our bearing. So we're gonna use a bearing for the shoulder. We could use a bushing. I want to use a bearing because I expect this to move pretty fast. So our bearings have an ID. The outer diameter is an inch and an eighth, so 1.125 of an inch. We have a specific end mill for the bearings. Basically, we just use that end mill and we just drill through the hole. Sorry, we drill through the material. But again, this is designed for CNC, so the CNC can pocket out this hole way more accurately than we could just plunge through it. So we're gonna use the CNC. Also, the OD of this bearing is you may have seen the bearing in this drawing, in this design. The ID of the bearing is an eighth of an inch. That's not the flange of the bearing. So here, let me make this transparent. So when I say the flange, I mean this part, and when I say the ID, or sorry, the OD, I mean this part. The OD fits into the hole that we just put, and the flange is to stop it from coming off of the shaft or moving on the actual shaft. Basically, the flange kind of constrains one side, so it can't move through the material. It could move off the material, but that's unlikely. Especially since we're going to put spacers on things. So this design doesn't have spacers on it, but a spacer would live here, a spacer would live here, keeping everything tight. So let's open up this. So yes, 1.125 of an inch. And one thing we need to draw in here is we actually need to draw the aluminum tube that's going to make up the arm. Why do we need to draw the aluminum tube that's going to make up the arm? So that we can set it, so we can set this bearing a specific distance away from this tube and be sure that it's not going to hit. So it's 2 inches. I'm going to draw it by 2 inch by 2 inch like a square. The only reason I'm drawing it 2 inch by 2 inch like a square is really just so I don't have to draw more of the tube than necessary. I'm going to draw a line with it so that you can see, you have an idea of, that's fine, I can make these perpendicular, of how the arm would, like what the arm would do when it swings, but it's not super important right now. Okay. So let's think about when the arm tube is its longest. Like when does it take up the most space in this perspective? Um, that's when it's on a 45-degree angle to everything else. So basically, it is the longest from this point to this point when they are horizontal to each other. Um, that means that we're really concerned about when this point is going to hit this here. When it's vertical or when it's completely horizontal, there's actually tons of space if we constrain it such that this point is a specific distance away from here. There's going to be more space because this distance, the center to center distance of this line to this line, is obviously smaller than the hypotenuse. If you know Pythagorean's theorem, the distance here is going to be way less than the hypotenuse of this line. The hypotenuse being like this distance being the equal length of this line. The hypotenuse is obviously going to be longer than that. So we can dimension this from here to here. I'm going to dimension them to be 20 millimeters is actually okay. That's pretty close to an inch. I want to go closer to half an inch. So I'm going to do 15 millimeters. I know half an inch is 12.7. So I can live with 15 millimeters. And that sets the center position of this bearing. Now, again, uh, yeah, this is for later, this line. So I'll leave that there for later. Okay. Now, a few things. We've figured out where we want to put our bearing. We know where we're going to put our bolt holes. Our next step is where we're going to put our gearbox and what is necessary in placing our gearbox. So obviously we need to understand the overall size of the gearbox and we need to understand where the bolt holes go for the gearbox. Um, we also need to consider the center to center distance of the gearbox to the pulley that is going to live on that bearing. So let's start with the gearbox. So this is the gearbox we're going to use. We talked about this last time. It's a Versaplanetary Gearbox. And I showed you guys the CAD that is given to us. So I know I have this in my design, but SolidWorks is going to be slower than just pulling up these drawings. So the distance between the bolts is 35.46 millimeters, and the overall width is 1.75 inches. I know that this width is smaller. Doesn't matter too much. I'm going to say the whole thing is 1.75 inches just because then I can rotate it in any which direction and not be worried. So let's start by placing a hole. I'm going to draw a rectangle. I'm actually going to draw 2 rectangles. So the first rectangle, I'm going to make it the 1.25 inches, the big rectangle, 1.75 inch, 1.75 inch, and then this was 35.46, 35.46, and 35.46. I'm going to make these 2 lines collinear so that these 2 shapes follow each other. And then I'm going to make this center line vertical so that it stands up 45 degrees to the frame. Now, right now, it is inside the aluminum tube, which is not ideal. We want it up here somewhere. So let's actually set this distance. I'm going to set the distance from the lowest point on the gearbox to the top of the tube. So this dot here to this line here as 10 millimeters, just so we have a gap. And I'm going to draw in some bolt holes in the slot. So I'm going to put a 4 millimeter bolt hole here. The Vex parts use Imperial Fasteners. I know a 4 millimeter bolt will not actually thread into the hole, but a 4 millimeter bolt hole will be sufficient for that hole in the gearbox, like for the bolt to go through, as like a clearance hole. Now I'm going to draw a slot. Actually, I can do that after. Now I'm drawing a slot so that we can tension our gearbox. Tension the belt for our gearbox. I'm going to make these 2 coincident. And there we go. I'm going to make this 2.5. I'm going to make it a little bit bigger than it needs to be, because this hole we could easily drill out. This slot would be difficult to like make bigger. We would have to like put it on the mill and pocket it out more, which would be difficult to do. So I'm just going to make it bigger than necessary. And I'm going to make this distance about 50 millimeters. Oh, that's too much. Let's go for 40 millimeters, and I'm going to actually move this point back. So Let me just undo. Where's that center point? Whatever, it's fine. It's okay the way it is now. Realistically, I wanted the radius to be actually a little bit bigger so that this is not as round. And then I could make it longer, but this is actually way more than enough because rotating it up to here would actually put a significant amount of tension on the belt regardless. So we're gonna live with this. So now what? Now we need to actually calculate the center to center distance. So I want to talk about a few things first. I want to talk about what pulleys and belts we have available to us, and then we can get into doing the actual calculation. So in terms of pulley, we're going to use HTD timing pulleys. They're a little bit more durable. We also have G2T pulleys. If you're familiar with 3D printing, your 3D printer probably uses a G2T pulley for its belts. G2T is a lighter duty pulley than an HTD timing belt. Um, that being said, the main difference is just the profile of the teeth. And beyond that, there's not too much. So Vex offers 4 sizes in 2 different sizes and 2 different widths. They offer a 9mm and a 15mm. We're gonna use the 9mm because it has the belt strength is the belt strength is more than strong enough, so it's perfectly okay. Now, a few things to keep in mind, like um like chains and yeah, like chains, the bigger the gear, like the bigger the sprocket, the less internal friction there is going to be on the chain. So when we use a smaller pulley, um, it's going to cause the belt to rotate faster around the pulley, which means there's actually going to be more friction and it's going to be less efficient. Now that being said, it's like unnoticeably less efficient. Like it'd be like 1% less efficient, which is nothing. Like if you remember when we estimated our gearbox, that was 65% efficiency for the gearbox. 1% less is like nothing. Um, Even a 1% gain is really nothing. Like that would save you got 300 watts, it saves you 3 watts. What? So we're gonna pick a specific pulley. Now, all these two timing pulleys. Okay. So here are the different sizes of pulleys. Now, we could use one of these huge pulleys, and I'll show you why we won't use one of these huge pulleys. We're going to actually use the 24 tooth pulley specifically. But the huge pulley has a 57.3 inch, 50.7, 57.3 millimeter diameter. Now, if I draw that, what do you notice? The pulley is covering our bolts, the bolts that make up the gearbox, which means can't tension our system anymore, which is less than ideal. So this pulley is too large, and this is also just the pitch diameter. This is not actually the overall diameter of the pulley. The overall diameter, like the outer diameter, is actually much larger, about 3 millimeters larger. So we're gonna go for a smaller pulley. We're gonna use the 24 tooth, which is 38.2. So 38.2, and you can see it's significantly smaller. Now, just to prove that we can still tension this, draw another circle, make it 42 millimeters. And you can see we still have a lot of clearance to our bolt. So that means we can get our socket head, our Allen key in there to tighten or loosen the bolt, which means we can now add tension to our belt, which means we don't have to design or manufacture this to be as accurate as before. I'm going to draw the other pulley in here, just for the sake of drawing it. I don't need to, but just because. So 38.2. And now, basically, all that's left for this design, for this concept sketch, is to figure out what the center to center distance is of these two gearboxes. So if you bear with me here for a second, I need to plug in something and open up MS Paint. And we're going to draw some pretty pictures. So Now we're in MS Paint. I'm going to move myself over here. I'm going to start by drawing 2 circles. Oh, that's not a circle. I'm going to start by drawing 2 circles. So here's circle 1. And here's circle 2. Now, a few things to keep in mind. When we're calculating the the belt, what we're really concerned about is the center to center distance, which is, oh my god, these are not straight. Center to center distance, which is this distance here. We're also concerned with the overall diameter of the pulley. So this distance here, because we need to calculate circumference. And really the way it works is we want to calculate one distance. Why is it so small? One distance around this pulley, the length over to here, and then the distance around this pulley and the length back. They call this the loop length of the belt. So what we can actually do, there's a really simple calculation that we use to find the loop length of the belt. We can work that calculation backwards to find the center to center distance. So if I move my keyboard out of the way and put my drawing tablet in front of me, I'm going to change my color to blue. So I'm going to refer to the overall length as the loop length, the center to center distance as CC, and this as the diameter. I could call it the pulley diameter, but I'm just going to call it the diameter. So the loop length is equal to 2 center to center distances plus, not 2, plus pi. That's not pi. That's not pi either. That's pi. Pi d. Because we have a half circumference here and we have a half circumference here. Which means overall that's a full circumference. Fancy. So we can change this equation to be solving for the center to center distance. So we're going to say loop length minus pi d divided by 2 is equal to center to center. Perfect. So now with the given loop lengths that we get from the Vex website, I'm going to put this here like this. With the given loop lengths from the Vex website, which I'm going to pull up here in a second, from these belts, we can figure out what an optimal center to center distance would be for our gearbox. So the first one, 300 millimeter pitch. Let me pull up my calculator. Now, I'm going to start by calculating the circumference of the pulley. So 3.14 times 38.2. 120 millimeters. I'm going to round it up to 120. I'm rounding up like 0.1 of a millimeter. If you know what 0.1 of a millimeter works like, you'll understand. It's nothing. So 120 millimeters for our circumference. So if our pitch length is 300, we subtract 120 and we divide by 2. So our center to center distance, 90 millimeters. Let's set that in CAD and see what that looks like. So if I set this distance here and this distance here, this point, to 90, it's going to move it nice and close. Now, this is not ideal actually, if you think about it. This arm needs to swing, and now the gearbox is actually in the range of motion of the arm. If this arm swings all the way around, it is going to hit the gearbox, which is not hot at all. So watch. It'll swing. Oh, 1 second. Sorry about that. So let me see if I could do this. I think you get the idea that it'll swing into the gearbox here. So actually we're not happy with this length. So the next one is 350 millimeters. So let's do 350 minus 120, which is 230 divided by 2. 115 millimeters. 115 is going to put us somewhere over here. So let's do that. 115 millimeters. You can see now it's well within the range. It's not going to hit the arm. It's not going to become an end stop for our arm. It's actually in a nice position. It kind of overlaps this line here just a little bit. Probably a little, like not enough. Like if we were going to draw this gearbox plate up, we'd actually want it more to this left. So let's make this longer because we can. So 20 millimeters here. So I'm actually gonna live with this 350 millimeter belt. Um, this is a good length. The center to center distance is nice. It's gonna yield us a small design, which is good. So let's finish up drawing all the parts of this. So I'm gonna draw a few lines here. I could have just drawn a rectangle, but I'm drawing them like this for a specific reason. Really, it's just gonna make it easier for me. Make these two collinear. So this line is now vertical. And you can see that the outside of the plate gives me plenty of space to this bolt. I'm actually going to take this line here and make it coincident with the top of the gearbox so that they are like nice and close to each other. I'm going to set a specific distance from the center of the bearing to this line. Now, I'm going to do about 30 millimeters. Um, I could do about an inch. 30 millimeters is more than an inch actually. So this is a nice manufacturable number for us. And really, that's all there is to it. I'm going to put a nice line, like a nice cut down the side here, um, just to remove some unnecessary material. What I'm going to do is I'll make it parallel to this square here. I know this is at 45-degree angle, so now this is also at a 45-degree angle. And I'll set it a specific distance from this here. I'm going to set it the same distance, actually, so I'm going to say 30. And really, that's all there is to it. I'm going to turn this actually into extruded part now. And this will be the last thing that we do today. So, bear with me because there's a lot of lines here. So this is going to get ugly. The only hole that's important, and I didn't properly set the size, so we'll go back and set the size, is this center hole. And there we go. I'm going to make this plate a 1/4 inch. Aluminum is pretty common. So I'm going to say 1/4 inch. And here is our plate. Now, this hole size is not correct. I'm just going to edit it really quick. So how I'm going to set this hole size is pretty straightforward. I am going to draw the 1/2 inch hex shaft inside of it. And I'm going to use that to set the size of the hole. So 12.7 millimeters is not 127 millimeters. My typing skills are not on point today. It's okay. So you can see right now the hole actually overlaps. Let's go for 17. And now we got lots of space. So that's enough clearance for that hole, for it not to interfere with the shaft. And this is our plate. So as you can tell, this resembles the plate that I used here. Obviously, this plate that I made here has like weight saving measures. That's what this is. But beyond that, they're more or less identical. They're functionally identical for sure. This one has a few more cutaways. These are just fillets and stuff to make it look prettier. And really, that's all there is to it. If you made it this far, thank you for sticking around. I'll see you in the next part. Thank you for sticking through the technical difficulties that we had this morning too. Hopefully we don't have them again next time. And